Okay, welcome to the lecture 11 of Classical Mechanics 1. Today I'll continue with the calculus of variation. And Hamilton's principle. So, before I begin today's lecture, let me know if you have any doubts or anything you want me to repeat or re-explain in the discussion forum. So, I will address your queries, questions and doubts. In last few lectures, we are discussing if the constraints present in the system, how one can find the equation motion of the system. So, let me start with that. Constraint imposes two types of problems. So, one is that all variables are not independent, and second problem is that the force of constants a priori. Okay. So, if beforehand we do not know what are the force of constants, so we will not able to deal with them. So, and if the constant is there, all dynamical variables, all the coordinates are not independent in the system. So, you have to careful or you have to deal these two problems. So, first we started with that, how we can deal the second problem, and I suggested in my previous lectures that this can be handled through the D'Alembert's D'Alembert's principle of virtual work. What is the principle? So, the principle was that the virtual work done by all force of constant are considered 0, and that leads to that principle leads to the equation of motion which we called D'Alembert's equation. And that equation was ddt of del t. This capital T is the kinetic energy of Qi dot minus del T del Qi equal to Qi for I equal to 1 to small n, the number of degrees of freedom in the system. And these Q's are independent variables. Okay. So, now this T is the, let me complete, T is the total kinetic energy of the system. So, it is sum over all particles. Now, these particles are n particles. So, half m I Vi square, and Q is the generalized force. We define force, and one has to find all this equation. So, this is the D'Alembert's equation, and this equation was obtained by considering that virtual work done by all force of constant is 0. From there, that principle we obtain this equation motion. Now, let me repeat, the virtual displacement is the displacement in the coordinates which is consistent with the forces and constraint of forces, and it happens in no time, instantaneously. So, the difference with the real displacement takes some small time interval, and it is possible that during that time interval the forces and the constraints dynamically change, evolve with time. So that is why we consider virtual work done, and then the effect of constant forces, effect of constant we consider, and through that we obtain the equation which I just wrote here. So this equation. Okay. So now then we proceed to if we have the first type of problems, that we have holonomic systems and we can eliminate our coordinates to find the generalized coordinates, and there we can apply Hamilton's principle. So let me just remind you what was the Hamilton's principle. So Hamilton principle had two parts. So part 1, which introduce a mathematical quantity known as Lagrangian. So this quantity is function of all generalized coordinate, time derivative of the generalized coordinate, that is generalized velocity, and time. So first principle says that all mechanical system characterized by a definite function of generalized coordinate, generalized velocity, and time called Lagrangian of the system. So first Hamilton's first principle, part 1, introduce a mathematical quantity which is function of generalized coordinate, generalized velocity, and time, called the Lagrangian of this. Now the second part is more important. It gives that what will be this Lagrangian such that we can find the equation of motion. So second part says that a mathematical quantity called action, which is just a line integral of initial time to final time of the Lagrangian, just introduced in the part 1. So this quantity should have extremum, will be extremum along the path. Path of evolution. So a classical system is represented by a point in the configuration space. So let us say this is my configuration space, and initially the system is here, so initial, and finally this system is here. So this how the system will evolve from here to here. That means the number of ways you can connect these 2 points, and 2 points can be connected by infinitely many ways, right? And for each way you can calculate this mathematical quantity action, which is a line integral of the Lagrangian between the initial time to final time, between these 2 points, initial point and final point. So there will be many action, but classical system will evolve through that path where delta S will be 0. That means action will be extremum. So that using this condition we have to find equation of the system, classical system. So but to extremize this action, now you can see that it is a function of the functions kind of thing. So we need to know little bit about calculus of variation. So in the last lecture we started discussion on that calculus of variation. So calculus of variation we have started, and we have seen that if you have a functional, say f y dot and x, where y is function of x and y dot is dy dx. So f is a functional means function of function. Now we want to extimize under which condition we want to extimize a quantity j, which is a function of these variables, integrate over some initial point to final point. So we for different paths connecting between okay, let me go to my earlier pages, because so suppose we want to calculate, extimize this quantity j, which is just a function of integration over some initial point to final point of a functional which is like this dx. Between the point, the all possible path connecting x1 to x2. So to count for all paths, we parameterize. If you recall the last lecture, we parameterize your y as by introducing a parameter alpha, such that it is at alpha equal to 0 plus alpha times eta x, where this eta x is a well behaved non-singular function, okay, and continuous function. So then we will find that extimization condition will be del j del alpha. So by varying alpha, we can have different paths, and under which path alpha will be extimum will be given by this condition, and using this condition we derive a equation which is del f del y minus ddx of del f del y dot equal to 0. So this equation we derive. So this is the recap of last lectures, and now okay, before we go to that some application of calculus of variation, let me tell this equation is known as Euler's equation. Okay, and for the advanced study, I give you a homework that find so advanced question, find the second form of Euler's equation. It can be re-expressed in different ways. So there is also known as second form of Euler equation. So find that is your homework. So now we will consider one small example to illustrate this principle of this variational calculus, that how we consider that extimization of a functional and extract equation from there. So suppose I ask this problem to solve. So this problem is that find the trajectory of shortest path on a plane. Okay, let me explain that. Suppose you are going from one point to another point in a plane, which will be the shortest path? What will be the equation of motion for the shortest path? This is the problem, and this is also a problem of extimization, that you have to calculate distance between these two and then extimize that for which path the distance will be minimum. See, extremization problem is used in many places. So one can have suppose you want to travel from one place to another place. So there are some softwares who can ask that whether you want to reach there in shortest time, whether you want to reach in the cheapest way, or the fare will be the minimum, or the time taken will be minimum. So depending on that condition you can extremize. So extremization has many examples you can find. There will be many problems you can solve using this method of variation calculus, which gives you the how to extremize a functional. Okay, so let us the distance element in the plane, we can write ds is the square root of dx whole square plus dy. So I characterize my plane with the plane is characterized by x and y. So the distance element I can write square root of this, and then the total distance between the point x1 to x2. So you are moving from a point, say x1 y1 to x2 y2. Okay, so you can have various path. Okay, so this total distance I'll write I say will be integration over some x1 to x2 and say ds, or x1 y1 point to x2 y2 point, this. So which I can write as integration square root of 1 plus dy dx whole square times dx, and this integration is between x1 to x2 because x changes from x1 to x2. Okay. Now we will see that after so here analogous to our earlier discussion, that f function which I was discussing, the f function is here is just 1 plus y dot square, because y dot is dy dx. So your earlier f function is this, and then the extremization condition, if you recall the extremization condition, we obtain ddx of del f del y dot minus del f del y equal to 0. So this was the extremization condition. Okay, so now let us calculate this simple thing. So df dy dot is basically half root 1 plus y dot square and 2 y dot. So it is basically y dot by root over 1 plus y dot square, and df there is f does not depend on y, so df dy equal to 0. So this condition for extremization leads to ddx of y dot root over 1 plus y dot square equal to 0. So this means that y dot root over 1 plus y dot square is constant. So this implies if y dot plus root over y dot square is constant, y dot is constant. Okay. So if y dot is constant, then y equal to some ax plus b. So this is the path which will be have the shortest distance. So let me show in the picture that this path is given by a straight line. So in a plane, the shortest distance between two paths is straight line, and we obtain this result. We all know this result, that if you go from one point to another point in the plane, then the shortest distance will be the straight line, and that we proved using our result of calculus of variation. Now Now we are going to apply this condition to extremize our action. So now go back to the Hamilton's principle. Again, so second part of the Hamiltonian's principle, that we know a action. It was defined a action which was the initial time to final time of the Lagrangian, which is qi dot and t. Okay. So now we have learned that how the variational principle gave a condition or equation for extremize some functional. Now we will apply that variational principle to the Hamilton's principle to extremize our action. So action which was defined from the t initial to t final between this Lagrangian integration over dt. Okay. So now if you carefully look at that, so we have to find extremize this condition, that delta s equal to 0. The meaning is that classical path will follow classical system will follow the path in the configuration space for which the action S will be extremum. Okay. So that extremum means delta S, variation of that action, mathematical quantity, which is defined from T1 to Tf, the Lagrangian, which is function of generalized coordinate, generalized velocity and time, will be extremum. So delta S will be 0. So now if you look at that, our analogy between that extremization of that functional, which we obtain the j we extremize between the point x1 to x2 f y dot and x dx. So if we consider the analogy, this is nothing but our action, and f is nothing but our Lagrangian, which is function qi dot and t. Instead of one variable, we have now many variables depending on the degrees of freedom. So I varies from 1 to the degrees of freedom of the system. So how many generalized coordinate we have, and q, analogy of q, so y in the variational calculus problem, that is now with the qi, and qi dot y dot will be qi dot, and the role of t is x. So we apply the same technique, same derivation, and then we can obtain the equation for to extremize the action according to the second part of the Hamilton's principle, and we obtain this del L del qi minus ddt. Now ddt of del L del qi dot equal to 0 will be the, for all values of q, will be the equation of the path for which delta s equal to 0. So if L characterizes a classical system, so this will be the equation motion, since L characterizes the classical system. It is responsible for the dynamics of the system. This equation del L del Qi minus ddt of del L del Qi dot equal to 0 will be the equation motion the classical system, and this equation is known as Euler-Lagrange equation. Okay. So, this equation known as the Euler-Lagrange equation, and this describes the the dynamics of a classical system will be of the classical system by this equation. So, let us consider an example. Just suppose this equation, the Lagrangian of a system is given like this. Some Lagrangian for a 2 degrees of freedom q1 q2, 2 generalized coordinate, q1 dot q2 dot, and this Lagrangian suppose given like this, half m q1 dot square plus q2 dot square plus say q1 dot q2 dot minus half k1 q1 square minus half k2 q2 square. Suppose some Lagrangian is given, and we will use that what the equation of motion we can obtain from this Lagrangian, where m, k1, k2 are constants. So, let us find the equation, because I already mentioned that you have to find equation for all values of I equal to 1 to the degrees of freedom. In this case it is 2 degrees of freedom, so we have 2 coordinates. So, del L del q1 dot we can calculate, it will be m q1 dot plus q2 dot. Okay. So, ddt of del L del q1 dot is m q1 double dot plus q2 double dot, and also we find del L del q1, which will be minus half k1 to q1. So, minus k1 q1. So, the equation of motion will be m q1 dot plus q1 double dot q2 double dot plus k1 q equal to 0. So, if the Lagrangian of this form, then the equation of motion will be this. Similarly, you can find for q2 also, which will be m q2 double dot plus q1 double dot plus k2 q2 equal to 0. Okay, so you can verify easily. So maybe with this we'll stop here. In next class we'll see how these equations, this Euler-Lagrangian equation can be used to find the equation motion for different system. Before that, we have to know the various properties of this quantity, mathematical quantity, which is very, very important for this course, that Lagrangian. So in next lecture we will start with the properties of Lagrangian, and then we will construct some we will consider few examples to find the Lagrangian of a system, and what will be the structure of Lagrangian, and how to calculate for a system and find the dynamics or equation motion for a classical system. Okay, thank you.